This is a very useful application of the Railroad Commission for Texas. And here you can see all the wellbores that are drilled in Texas. So for example, if we went to, let's say, where do you want to go? Where do you want to take a look wellbores at? Let's do the case of the homework. It's actually of the test. It's Eagle Ford, and if I remember well, it was Frio County, so somewhere over here. So I keep on zooming up. When you zoom enough, you start to see the size of the leases, and then wellbores. All of these are vertical wellbores. The black lines are horizontal wellbores. So all of these are laterals. And the direction of the line tells you in which direction the lateral has been drilled. So all of these, you see, or all of those are laterals, 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 laterals. And notice that most of those, I shouldn't have zoomed out, most of those, they have a preferential orientation. That preferential orientation is the same as that one. It's the orientation that will maximize hydraulic fracture surface area, and it's going to be perpendicular to the expected plane of hydraulic fractures. In this case, it's normal faulting. This direction is the direction of which direction? Which stress? SH mean, right? SH mean. So by looking at these maps all over Texas and all over the world, and you can see by indirect evidence what is the orientation of SH mean. And this is exactly what you have in this problem. You see the direction in which the laterals are being drilled. Your objective is, based on that map, to justify what is the most likely orientation of the horizontal stresses. This plot is a little version of that one, but it's exactly the same thing. If the wells are drilled in this direction, that means that SH mean is coming at this orientation, at an angle that, let's say here, I put here 30, right? But it looks probably more like 40, something like that. And based on that, you can tell what is SH mean, what is SH max, what will be the orientation of hydraulic fractures, and also what will be the orientation of faults, the expected orientation of faults under those conditions. That's something you do not see in here, but indirectly, based on the direction of SH mean and knowing this normal faulting, you could say that, you could tell that. And this is the same as before. Go to stereo nets and plot those fault orientations. Something very important. There was a mistake here. In the version that I uploaded, it says 300. It should be 210. Okay. And you may ask, why is it 210 and not 30 degrees? The reason for that is that usually you measure strike using what we call the fault coordinate system, where, let me move this a little bit more to the left. In the fault coordinate system, first element is deep, second element is strike, and third element is normal. So if I were to go to fault number 1, this would be, remember, the first one is direction of the deep. So it will go like that. And this will be direction of the strike. It will be an arrow that it's pointing in that direction. This one is deep, this one is strike. So the angle between the north and that is 30 degrees. However, for the second one, if now I follow the same thing and deep is going down like this, now this is strike. And the strike is an arrow which is pointing in that direction. So the angle of that is going to be 180 plus 30. That's if you are using this coordinate system. But if you told me that this is equal to 0, 30 degrees, that's still fine, okay? So don't worry much about that. If you were to put this into the equations that we put about calculating stresses on faults, then you really have to put that angle. But conceptually, this one is still okay. So if you still have some questions about the stereo nets, I strongly recommend that you check that online app for which I sent a link. There you can see very well what is the meaning of those points, rotate that in 3D, and see that much better than what I could do over here. Okay. Problem number 7. It's a problem of determination of horizontal stress based on failure, but the previous one was about normal faulting on top of a salt diapier. This is a case of a sedimentary basin next to mountains, next to very high tectonic strains. So in this case, what we want to do is to estimate what is the maximum value of SH max. And in order to do that, you calculate SV, you calculate sigma V, you calculate your friction coefficient Q, which comes from the friction angle, and out of that, you calculate sigma H max. At pore pressure, you get horizontal maximum stress. And in this case, additionally, you have to draw a Mohr circle. What would be the inverse way of solving this problem? Sometimes, do you think we can run tests on measuring friction angle of faults? Not very likely, right? That would be a very, very large experiment and cannot be likely done. So something that you could do instead of this, in order to estimate this parameter, you could say, okay, I'm going to measure my SH max by, say, breakout angle determination. I'm going to measure my sigma V because I know sigma V. If I know SH max, I know SV, I know pore pressure, and I know those effective stresses, I could tell what Q is out of this equation. It will come out of this equation, right? And if I know Q, I can also find an equation that tells me what is the friction angle. And that will be like the equivalent large size or large scale friction angle of the faults. That you get it indirectly by knowing what are the stresses by some other methods, and then you back calculate this number. And probably you can use that number in some other location in which you do not know what your stresses are. All right. Any question about this one? No? We're over time, but this one is almost exactly the same as the one before, just a horizontal wellbore. Okay, guys, very important. I'm going to be in my office from 4 to 5:30. Okay, I have a visitor at 5:30, so I cannot stay longer. But I'm going to be there if you need help.